Let's begin our quest for the various sources of volitional control by looking at a human brain. Here in my hands, I have a model of a human brain. It's painted so that those areas of the cortex that have a similar microscopic neuronal architecture are marked the same color. Mapping this out was the life's work of a German neuroanatomist called Corbinian Brodmann. Every part of cortex has an associated number such as Brodmann area 17 or 45, depending on the order that he arbitrarily investigated its neural architecture. These little numbers just say which number each of the uniquely colored Brodmann areas is. Now, this is the front of the brain. The frontal lobes are under our foreheads. This is the back of the brain, or the occipital lobe, where visual input enters cortex. Here we see the temporal lobes. And here on top we have the parietal lobes. This is the underside of the brain. Here you can see the cerebellum. If we separate the left and right hemispheres, we can see the medial surface of the cortex. Here you can see the corpus callosum, the brain stem, and here you can see the thalamus. Our goal is to learn about the executive control systems of the brain, especially those that allow the brain to take volitional control of how it will behave via the body, or volitionally govern itself, such as what it will pay attention to even in the absence of an overt movement of any part of the body. As a general rule, the brain is divided into a perceptual processing side and an executive control or planning side. The divide between these two functional halves, perceptual or bottom-up, and executive or top-down, just so happens to fall almost exactly at the midpoint of the brain at this sulcus, called the central sulcus. Perceptual processing tends to run back to front, whereas executive processing tends to run front to back across the cortex. In the front here, in so-called Brodmann area 10, which is right under our foreheads, we tend to have the most abstract sorts of planning taking place. This might include plans that are independent of the present sensory input, such as, next year I want to learn Arabic. It might also process stacks of plans, such as, I need to go to the supermarket, but on the way I have to carry out the subroutine of going to the post office in order to buy stamps. And if I get interrupted, say because I run into a friend at the post office, it might remind me that I had better go to the supermarket before the kids get home. Or it might process a high-level proposition such as, I need to drink more water. Now, a bit further back, in so-called premotor cortex, a more concrete plan might come up with a particular path toward a particular water fountain. And by the time we reach all the way back to the motor strip, which lies in the gyrus just in front of the central sulcus, called the precentral gyrus, particular motor sequences might get activated. This might be thought of as pulling the strings on a marionette. In fact, you can think of your own body as your own personal marionette whose control is via the strings being pulled in motor cortex by other more anterior executive areas. In the case of vision, information processing tends to run from the back of the brain forward in various processing streams. Information that flows down the ventral stream flows down the temporal lobe. Ventral stream processing seems to be central to our conscious experience and object recognition. Sometimes people call the ventral stream the what processing pathway because it helps us know what an object is. It flows down the temporal lobe toward the hippocampus, where objects can be identified and stored for later recognition processes. Some of this bottom-up visual information is selected via attention for deeper processing. It's shunted toward frontal working memory areas where it can help frontal areas plan what to do next in light of what is being seen. There's also a dorsal stream flowing from visual input areas up into the parietal lobes. This information is not about what an object is, but rather it's about where it is and where it's going. So sometimes scientists call the dorsal stream the where processing pathway. Because of this division of labor into two or more processing streams, you might have a neuron down in the ventral stream firing away, carrying the information that there is, say, a tiger out there in the world somewhere, but I don't know where. And at the same time, you might have a different neuron up here in the dorsal pathway, firing away, carrying the information that an object of a certain size and at a certain distance from me is moving in this or that direction at this or that speed, but I don't know what it is. One problem is how the unconnected information in these two processing streams can be brought together so that we can know that it is a tiger at that location moving this way or that. This is one aspect of the so-called binding problem. How can information that has been separated into separate, parallel processing streams be brought back together into a unitary bound representation such as the unitary moving tiger of our subjective experience? It's a bit like the problem of putting Humpty Dumpty back together again. One idea is that attention binds the outputs of these two processing streams by creating a link in frontal working memory areas such that a new neuron in an area such as this one, called dorsolateral prefrontal cortex, temporarily takes input from a ventral stream tiger detector and simultaneously from a dorsal stream moving object detector. When such a frontal neuron fires, it's driven by both of these inputs and effectively becomes a tiger at that location detector. Thus, attention may play the role of a binding glue, linking across information processing streams. Before we leave our model of the brain, let me point out that there are many other processing streams than just the ventral and dorsal visual processing streams. There are analogs of the ventral and dorsal pathways for audition, touch, and the other sensory systems. In addition, there are other pathways even for vision. For example, here on the medial surface, there appears to be a medial processing stream involved in navigating through the world. Its information processing runs down into the hippocampus from this angle. Having multiple processing streams allows the brain to operate in and compute in multiple coordinate systems at the same time. The coordinate system of the ventral processing stream appears to be viewer-centered or egocentric, which is to say where things are relative to me, the viewer of a scene. In contrast, the coordinate system of the dorsal stream seems to be in effector-based coordinates, that is, where they are relative to an effector such as my hand, my head, my eyes, and so on. And the coordinate system of the medial processing stream appears to be in so-called world-centered coordinates, which is to say where objects are in the world relative to each other rather than relative to where I happen to be standing. Thus, just as we have many distinct specialist organs in our body, like the heart and the lungs, our brains appear to have many distinct information processing mental organs that specialize in different tasks.